Welcome! In today's episode we are going to discuss everything about our nearest star Sun, how it works, history of Sun, structure of our Sun, what role does Sun plays on life on Earth and its evolution across the cosmic timescale. How does the Sun work without oxygen? Have you ever stopped to wonder, how does the Sun burn so brightly in the sky, day after day, year after year, without ever running out of fuel? On Earth, a fire needs oxygen. Blow out a candle or cut off its oxygen supply, and the flame dies. Yet the Sun shines relentlessly, without a single whiff of oxygen in the vacuum of space. So how does it work? The truth is even more fascinating than we imagine. To understand, let's take a journey through the Sun's history, its inner workings, its cycles, and its future. The birth of the Sun. Around 4.6 billion years ago, long before Earth existed, our solar system was nothing more than a vast swirling cloud of gas and dust floating in the Milky Way. Over millions of years, gravity pulled this material inward, compressing it into a dense spinning core. As the core collapsed further, temperatures and pressures soared. Finally, the heat became so intense that nuclear fusion, a process far more powerful than any fire on Earth, was triggered. That moment marked the birth of the Sun, the star that would anchor the solar system, shape the planets, and ultimately allow life to exist on Earth. Unlike a campfire that depends on oxygen, the Sun's brilliance comes from a completely different source, nuclear reactions at its core. Fire versus fusion, why oxygen isn't needed. Here's the crucial difference. A campfire or a stove flame is a chemical reaction, fuel combines with oxygen, releasing heat and light. The Sun's glow comes from a nuclear reaction, hydrogen atoms are fused into helium under extreme pressure and heat. So, the Sun isn't burning in the traditional sense. It's not a fireball of flames needing oxygen. Instead, it's more like a gigantic nuclear reactor, steadily converting matter into energy. Fusion, the heart of the Sun. At the Sun's core, temperatures reach about 15 million degrees Celsius and pressures are unimaginably high. Under these conditions, hydrogen nuclei are basically protons, move so fast that they slam into each other and fuse, creating helium. This process, called the proton-proton chain reaction, dominates in stars like our Sun. Sometimes, heavier elements like carbon and nitrogen also play a role in a different process called the CNO cycle, but fusion of hydrogen is the main driver. Here's the magic, a small fraction of the mass is lost during fusion. Thanks to Einstein's famous equation, E=mc², that tiny bit of lost mass gets converted into an enormous amount of energy. Every single second, the Sun fuses around 600 million tons of hydrogen into helium. Roughly 4 million tons of mass vanish in the process, transformed directly into light and heat. That's the power fueling our skies and sustaining all life on Earth. The layers of the Sun. The Sun may look like a smooth glowing ball, but inside, it's a complex structure made of different layers. Core, the powerhouse, where nuclear fusion takes place. Radiative zone, here, energy slowly creeps outward. Photons, tiny packets of light, bounce around in such dense matter that they can take thousands, even millions, of years to pass through. Convective zone, in this region, hot plasma churns like boiling soup, carrying energy outward in great currents. Photosphere, the visible surface of the Sun, glowing at about 5,500 degrees Celsius. This is the sunlight we see. Chromosphere and corona, the outer atmosphere, where spectacular solar flares and the solar wind originate. The corona, surprisingly, is much hotter than the surface, reaching millions of degrees. Here's a mind-bending fact, the sunlight warming your face today may have started its journey in the Sun's core millions of years ago, bouncing around until it finally escaped into space. Once free, it only takes about 8 minutes and 20 seconds to reach Earth. Solar radiation and its journey. The Sun's energy doesn't arrive as just visible light. It comes as a spectrum, infrared rays that warm us, visible light that illuminates, and ultraviolet radiation that can burn skin but also drives crucial processes like vitamin D production. This steady stream of radiation is what keeps Earth habitable. Without it, our planet would be a frozen, lifeless rock. But there's balance, too much solar energy, and life would be scorched, too little, and life would freeze. The solar cycle, the sun's rhythms. The sun isn't constant. It pulses with activity in cycles lasting about 11 years. At solar maximum, its magnetic fields twist and snap, producing dark sunspots, massive solar flares, and coronal mass ejections, bursts of charged particles that can sweep across space. At solar minimum, the sun's surface is calmer, with fewer visible disturbances. These cycles matter. Intense solar storms can disrupt satellites, radio signals, power grids, and even astronauts in space. On Earth, they trigger dazzling auroras, curtains of colored light near the poles, caused by charged particles colliding with our atmosphere. The sun's environment. Unlike Earth's calm, breathable atmosphere, the sun is surrounded by a seething ocean of plasma. Its outermost layer, the corona, stretches millions of kilometers into space, glowing faintly but fiercely hot. From this region flows the solar wind, a continuous stream of charged particles. This solar wind shapes planetary magnetic fields, influences space weather, and even carves long comet tails pointing away from the sun. Without Earth's protective magnetic shield, this wind would strip away our atmosphere. The sun's role in life on Earth. The sun is not just a source of light, it's the foundation of life itself. Plants capture sunlight through photosynthesis, converting it into chemical energy. That energy feeds animals, and eventually us. Our weather, climate, and even the water cycle all depend on solar energy. Every breath of oxygen we take, every grain of food we eat, every drop of water we drink, all trace back to the sun's energy. The sun through human eyes. For ancient civilizations, the sun wasn't just a star, it was a god, a source of mystery and reverence. Egyptians worshipped Ra, the sun god. The Aztecs offered sacrifices to ensure the sun would rise. Early humans instinctively knew, without the sun, there was no life. It wasn't until the 19th and 20th centuries that scientists began to uncover its true nature. Astronomers used spectroscopy to discover that the sun is mostly hydrogen and helium. Then Einstein's equation gave us the key to understanding how mass could turn into energy. Today, space probes like SOHO and the Parker Solar Probe continue to unlock its secrets, flying closer to the sun than ever before. The sun's future. Right now, the sun is in its stable main sequence phase, middle age for a star. It has been shining for 4.6 billion years and will continue for about another 5 billion. Eventually, the hydrogen in its core will run out. When that happens, the sun will swell into a red giant, expanding so enormously that it may engulf Mercury, Venus, and even Earth. Its outer layers will be blown away into space, forming a glowing nebula. What remains will be the white dwarf. A small, dense stellar ember, about the size of Earth but with the mass of the sun, slowly cooling over trillions of years. In cosmic terms, the sun too is mortal. Final thoughts. So how does the sun work without oxygen? By harnessing the most powerful process in the universe, nuclear fusion. Gravity crushes hydrogen atoms together, fusion transforms mass into pure energy, and radiation carries that energy across space to us. The sun is not a fireball fueled by oxygen, but a nuclear furnace that has burned for billions of years and will continue to shine long after our time. Next time you step outside and feel the warmth of the sun on your skin, remember, those rays began their journey millions of years ago, deep in the heart of a star, powered by physics so elegant and powerful that it sustains all life on Earth. The sun doesn't need oxygen. It needs only hydrogen, gravity, and time, and in return, it gives us light, warmth, and the possibility of life itself. With the aim to learn about a new thing every time and get 1% better, we are concluding today's episode. In the end, hope you find this episode quite informative and interesting. We are committed to make the world that we live in more and more meaningful for each one of you. Thank you.